We concluded the previous episode with an overview of the vast evidence accumulated by Halton Arp and others, and vindicated by the initial images of the James Webb Space Telescope, that cosmological redshift is intrinsic, which thus falsifies the foundational axiom of Big Bang cosmology. I turn now to deal with the Webb First Deep Field, unveiled during a White House event on the 11th of July 2022. NASA's Associated News release states, "Thousands of galaxies, including the faintest objects ever observed in the infrared, have appeared in Webb's view for the first time. This slice of the vast universe is approximately the size of a grain of sand held at arm's length by someone on the ground. This deep field, taken by Webb's near-infrared camera, is a composite made from images at different wavelengths, totaling 12.5 hours, achieving depths at infrared wavelengths beyond the Hubble Space Telescope's deepest fields, which took weeks. In order to make sense of this image, we must take account of several matters. First, we know from the study of galaxies in our local universe that they come in a range of shapes, sizes, luminosities, and colors. At similar distances, some galaxies are smaller and some are larger. Some galaxies, especially dusty galaxies, appear redder, while others appear bluer. For a given size, some are more luminous and others less luminous. Astrophysicists expect variability among distant galaxies at every point in the Hubble flow. Secondly, the Webb First Deep Field is centered on a massive galaxy cluster, surrounded by stretched-out, curved objects. In the Standard Model, these curved objects are distant galaxies that are gravitationally lensed, making them appear larger and brighter than they would be in the absence of that lensing. Of course, in the electric universe, that effect is due to refraction through the neutrino sea ether that is denser around that massive galaxy cluster than elsewhere. Thirdly, humans cannot see the wavelengths of infrared light that were used to construct the image. Instead, colors in the visible range that we can see were assigned to the different filters and then combined to produce the composite image. The specified filters are circled in the assigned colors in the NASA graphic that you see on the screen. You can see that there is broad coverage in the range from 0.6 to 5 microns. Visible light extends down to about 0.7 microns. As you would expect, NASA's image processing team assigned blue to the shortest or bluest wavelengths, green for still longer wavelengths, orange for even longer wavelengths, and finally red for the longest wavelengths in the image. Fourthly, for some of the small, faint galaxies in the Webb First Deep Field image, or in the deep images released by the CEERS project, we do not necessarily know whether that small size in the image is due to the galaxy being physically smaller and closer, or larger and further away. Now, assigning a value to the distance of a galaxy or quasar can be confusing. In the Standard Model, space has been continually expanding since the Big Bang, and the brief period of exponential expansion, referred to as inflation. That means that the distance traveled by light emitted from an object increases due to the expansion of space while the light is traveling on its path to the observer. Moreover, the space already traversed by that light continues to expand while the light continues to the observer. So a galaxy that is 1 billion light-years distant from Earth at the time its light is emitted will be further away by the time that light arrives at a telescope. The look-back time or distance at the time the light was emitted, plus that additional distance arising from the expansion of space during the light's travel time, is referred to as the, quote, co-moving radial distance. The dotted line marked distance now on the graph, and can give a distance in light years that exceeds the age of the universe, the horizontal blue line on the graph. The time that has elapsed since the light was emitted is referred to as the look-back time or light travel time, and is the value that is most commonly used to describe the distance of high redshift objects. That is what is shown on the y-axis of the graph. Notice the declining slope of the distance then line in this graph beyond a redshift of about 3. In everyday life, we're used to the intuitive idea that the apparent size of objects, what astronomers refer to as their angular diameter, decreases as the distance to those objects increases. An object looks smaller as the distance to that object increases. In standard model cosmology, that relationship only holds until redshift reaches about z equals 2. It's uncontroversial that in the expanding universe of the Big Bang, there's an optical effect that beyond a redshift of about z equals 2 causes the apparent size of galaxies to increase with increasing redshift and distance. This effect is totally counterintuitive, but is an inevitable consequence of Big Bang theory. This effect occurs because in an expanding universe, the light we see from high redshift galaxies was emitted many billions of years ago, when the universe was much smaller and the emitting galaxy was much closer. In the time that the light has taken to travel the distance to our telescopes, the space through which the light has traveled had continued to expand, reddening that light and reducing the amount that arrives per unit time. This leads to the counterintuitive result that beyond a redshift of about 2, galaxies of the same size will appear larger, redder, and fainter as their redshift increases. Moreover, as several Japanese scientists have shown, some red spiral galaxies with a redshift in the range of 1 to 3 can imitate galaxies with a much higher redshift. Finally, and perhaps most importantly, it is essential to recognize that the Webb first deep field is not claiming to depict redshift. Redshift values for objects across the image are not yet publicly available. Nevertheless, given the way that colors are assigned in the image, averaged over the whole image, the colors in the image are a reasonable proxy for redshift. So if the Big Bang theory is correct, then averaged over the whole of the Webb deep field images, and putting aside obviously lensed objects, the faintest objects should be the reddest objects in the image. Further, the faintest and reddest galaxies should appear larger than less faint and less red galaxies. But this is not what the Webb's first deep field and the Sears images show. Instead, it is plain on even a casual analysis of those images that, averaged over the whole image, the faintest objects are the smallest objects, and that a large proportion of the faintest objects are rendered in blue. We're going to look at a portion of the image indicated by the white rectangle. The arrows point to examples of faint objects that have been rendered in blue. As we zoom and pan across the image, note that a clear majority of the faintest objects, all of them galaxies, are rendered in blue. This is prima facie a stunning contradiction of the Big Bang's foundational premise. In the electric universe, space is not expanding. The universe is of unknown age and unknown extent, possibly infinite. Following the observations and insights of Halton Arp, one way new galaxies are formed is by ejection from active galactic nuclei, commencing life as very highly redshifted quasars that progress through quantized decreases in redshift, such that high redshift is an indication of the youthfulness of a galaxy. In the electric universe, we expect to see galaxies that get smaller and fainter, some bluer, some redder, to the limits of the telescope's observational power. That is exactly what Webb's first deep field shows. I predict that deeper Webb images will further confirm that fact. In particular, I predict that when very deep Webb images are obtained, with many days or weeks of observation, the detection of additional faint galaxies will simply show more of the same. And it only gets worse for the standard model theorists. According to Big Bang theory, the earliest galaxies are the least evolved galaxies. They have not had time to evolve and grow by accreting further gas and dust from the intergalactic medium, or through collisions, mergers, or the cannibalizing of smaller galaxies. Overall, and putting aside the so-called lensed objects for a moment, the reddest objects visible in the image should generally exhibit the least amount of smoothness and symmetric structure. Once again, that is not what we see in this image. Instead, overall, we repeatedly see smoothness and symmetric structure in the reddest objects, including especially the curved, so-called lensed galaxies. The arrows in the image on the screen point to a selection of the reddest objects in this portion of the image that bear out that contention. This fact is evident across the whole image. As for the red, so-called distant, lensed galaxies of the Einstein cross type, Halton Arp explains in an article on his official website titled Origins of Quasars and Galaxy Clusters that two higher redshift galaxies are found almost perfectly aligned across a lower redshift galaxy on either side of it. He wrote, "This, of course, is the quintessential pattern of AGNs ejected from a larger galaxy, often interpreted as gravitational lensing. We see the red, so-called lensed objects with so much visible structure in them because they are recently born and close to their low redshift parent. The universe that the Galileo of Palomar observed has biological overtones. We see families of galaxies and clusters in a small part of a universe of unknown size." Arp concluded that to prevent collapse in a non-expanding universe, gravity must be a repulsive force between celestial bodies. Collisions are in fact avoided. I have explained elsewhere the electrical nature of repulsive gravity between celestial bodies. The infinities beloved of mathematicians disappear when the distance between the centers of mass of two bodies on a collision course approaches zero. Nature must be explained by physics. Mathematics might describe the result. There are no collapsed matter objects in the universe, no white dwarfs, no neutron stars, and definitely no black holes. The phenomena can only be understood in a balanced electric universe. It is impossible to overstate the significance of these facts, facts that are plain for anyone to see on the face of the image. In short, this one image, Webb's first deep field, falsifies the Big Bang. And given that the Webb Space Telescope has a vastly improved spectroscopic performance, we can expect the spectra of high redshift objects will not match that expected from the story of heavy element production by successive generations of stars since a Big Bang. So-called lensed galaxies, that is, galaxies that do not appear as a result of refraction through a denser neutrino sea, are newborn high redshift quasars. They are the infants of nearby galaxies. Their faintness would not allow us to see them, much less their internal structure at cosmological distances. Being nearby, they will show anomalous superluminal motion when viewed conventionally, billions of light years away.